Alright, so I'm going to read this to you, so just relax, and if you want to see the photos and stuff, you can check it out that way, but mostly this will just be a straight reading. I might add some commentary, but let's get to this. I want to make it succinct. So this is train lighting batteries, Edison. You can see the old AC I guess we call them telephone poles, but power poles. And this manual's from 1916, 1916, over 100 years old. So the copyright is in the public domain now. And that's the trademark. Edison storage batteries. Thomas A, which stands for Alva Edison. Trademark. No price. Copyright 1916 by the Edison Storage Battery Company, Orange, New Jersey, United States of America. Form 118-6-16. Train lighting batteries, Edison. Bulletin 118. Edison Storage Battery Company, Orange, New Jersey. It's a photo of Thomas Edison. Photo by Falk, Falk. Copyright 1904, 1904 by the New York Edison Company. Edison train lighting batteries, a prophecy fulfilled. I believe time will prove that the alkaline storage battery will produce important changes in our present transportation systems. Thomas Alva Edison. 100 railways and more are using Edison alkaline storage batteries for train lighting or signaling or both. Electric vehicles equipped with Edison batteries have proved to be the most economical method for the solution of hauling and delivery problems in cities everywhere. Edison-equipped electric baggage trucks, electric industrial trucks, and electric tractors are making record reductions in the cost of handling baggage freight and material in and about railway terminals, about railway shops and industrial plants, at wharves, and wherever they are given the opportunity to show their advantages over the hand truck. The Edison alkaline storage battery for mine locomotives, for lighting and wireless and marine service, for lighting summer homes and farmhouses are not reached by central station lines, and for whenever there is a demand for a dependable reservoir for the storage of electric power or light, all bear striking testimony not only to the fulfillment of this prophecy, but to the complete adaptability and correctness of the Edison alkaline principle in storage battery practice. 7 years ago, magazines and newspapers announced the Edison alkaline storage battery as another contribution by Thomas Alva Edison to world progress and predicted that this invention would be of as great moment as his incandescent lamp. The million-cell plant of the Edison Storage Battery Company at Orange, New Jersey. It's now been converted into upscale apartments and the like. The reluctance on the part of the world to accord instant favor to new inventions is well known, especially to those that are so radically different in principle and construction, as the Edison alkaline storage battery is different from all the other batteries. Therefore, it will be interesting to know that the rapid adoption of the Edison alkaline storage battery to the many applications referred to above made it necessary to build the large concrete factory shown on page 6, 4 years after this wonderful battery had been placed on the market. The fact that over 100 railroads use the Edison alkaline storage battery for train lighting or signaling or both, and that some roads buy it exclusively, leaves no room to longer question its value. It is now an essential factor in railway economy. We would call your attention to its principal construction characteristics and numerous advantages it has demonstrated and to what it has done. Time alone contains the complete answer to what it will do, for Edison alkaline storage batteries that have been in service for 6 and 7 years are still giving full rated capacity. On the pages that follow, we shall endeavor to supply railway men with some of the definite knowledge regarding the Edison alkaline storage battery so that we may be better understood when we claim the Edison alkaline storage battery to be a simple, practical, money-saving, lightweight, long-lived, disease-free battery, easy to install, to understand, to maintain, and to operate. Our engineering department is always ready to cooperate with railway engineers and to give the benefit of its experience where it may be of assistance. Edison Storage Battery Company, June 1916. Type A8H Edison cell. Edison train lighting batteries. Train lighting by electricity to be universal. At no time in the history of railroad development has greater effort been made than now to attract the traveling public through the appeal of safety and comfort. And one big help in the success of this appeal has been the electrically lighted train. The electric lighting of parlor cars, sleeping cars, buffet cars, dining cars, coaches, postal cars, baggage and express cars, etc., possess a high safety-first factor since it makes the chance of fire, in the case of wreck, a very remote possibility. Convenience and comfort result from the steady, brilliant electric lights, which are odorless, possess a minimum amount of heat, and which may be used as berth lights in sleeping cars or placed in any position in a car where they may be most convenient. The electricity may be also used to run fans in the dining and parlor cars. The rapid increase in the number of electrically lighted cars in the United States and Canada bears out this idea and clearly indicates the approach of that time when the lighting of trains by electricity will be a universal practice. Furthermore, experience is daily proving that the successful method of lighting railway cars by electricity depends in such large measure on the service value of the storage battery that the selection of the most efficient battery is of vital importance. In fact, the storage battery may be truthfully called the heart of the system. It's only a one-man job to pull Edison batteries out for inspection. The Edison Alkaline Storage Battery. In the brief condensed description of the Edison cell which follows, we shall endeavor to define the many points of its superiority, points which 7 years ago were based principally on private experiment, but which are based today on the hundreds of thousands of Edison batteries and railway and other service throughout the world. The Edison principle is totally different from that of all other storage batteries, which are based upon either the Planté or Fior theory. They use lead peroxide or spongy lead in an acid electrolyte. Mr. Edison chose nickel hydrate for the positive active material of his battery, iron oxide for the negative active material, and an alkaline electrolyte. Note: for a brief description of the chemistry of the Edison cell, see page 28. The main advantage of this radical departure from old-time methods is more fully set forth in an address by Dr. Charles P. Steinmetz, extract of which appears on page 29. In brief, the Edison principle permits an all-steel construction and the production of a battery of superior ruggedness, longer life, lighter weight, and absolute freedom from disease. There is nothing about it to bend, buckle, or crack. It may remain in a charge or discharge condition indefinitely without injury. About the only care necessary is sufficient attention to keep the cells clean and to keep solution level above the tops of the plates. These are some of the characteristics of the Edison battery, which have been strong factors in establishing the Edison feature of low cost of battery maintenance and operation. Weight. The advent of all-steel cars, necessitating the building of stronger bridges, heavier locomotives, and heavier rails, is one big reason for taking advantage of every possible opportunity to save weight. In this connection, let us consider the weight of a 25-cell, 30-volt, 300 ampere-hour Edison alkaline set as compared with a 16-cell, 30-volt, 300 ampere-hour set of other batteries. The Edison set weighs not over 880 pounds. The other battery will weigh on the average about 2,880 pounds, making it a clear saving in favor of the Edison alkaline storage battery of approximately 2,000 pounds on 30-volt equipment and 4,000 pounds on 60-volt equipment. Then, too, it costs money to haul weight of any sort. Therefore, every pound saved must effect a saving in operating expense. Since this cost will vary with different roads, we must leave it to the operating department of the railway to figure what it costs to haul 2,000 to 4,000 pounds superfluous weight per car. It can be easily figured that this saving in weight alone enables the Edison battery to pay for itself. in from 1 to 3 years, depending on the per ton mile rate based as the cost of hauling passenger trains. Edison batteries assembled in 3-cell trays weigh only 100 pounds and can be easily handled by one man. In addition to the saving in haulage costs, the reduced weight of the Edison battery will show considerable saving in the cost of handling batteries at terminals. Edison batteries assembled in 3-cell trays weigh only 100 pounds and can be easily handled by one man, as shown above, whereas it takes 3 men to handle a double compartment tray of other batteries weighing 350 pounds. Recently, a certain railway, exclusive user of Edison batteries, desired to repaint 12 sets of batteries operating in 12 of its cars without taking the cars out of service. It was also desired to renew the electrolyte in some of the sets. The place where this railway has its shops is not a terminal, but all passenger trains stop for 10 minutes for engine changes and general inspection. While one car was taken out of service for its annual shopping, its batteries were removed and repainted. Then the repainted batteries were exchanged for a set on a car in service while the train was laying over 10 minutes at the station. This operation was continued until all the batteries were repainted. The ease in handling the lightweight Edison battery is well suggested by the fact that the average time for making this change on all cars was 6 minutes per car. This Edison feature enables this road to operate electric lighted cars without extra sets of batteries. Maintenance and operation. In addition to the saving in weight is the big saving in the cost of maintenance and operation. The electrochemical principle of Edison batteries makes them absolutely free from disease. There are no sulfated plates to require special treatment. The manner in which the active materials are held in perforated steel tubes and pockets eliminates washing out sediment. The sturdy steel construction of the plates assembled in a steel container leaves nothing about the Edison battery to buckle or crack. Hydrometer readings are not necessary except at long intervals of service to determine the gravity of the alkaline solution. Contrast the annual cleaning of other batteries with the changing of electrolyte in the Edison, which with proper care would not be necessary at intervals from 2 to 3 years. Even this does not necessitate the removal of the battery to a battery house, as the renewal of the electrolyte can be made on the platform or on the ground beside the car in about 1 hour. So, a little note here. This is before Edison discovered the addition of lithium. I think that patent of his is a little bit after this book was published. So that explains why the 2 to 3 years, possibly. It's something to check up on. That would just be potassium hydroxide and no lithium with the alkaline solution. The remainder being distilled water. This exemption of the Edison battery from an annual retirement to a battery house for cleaning and repairs makes the extra sets incident to the care of other batteries unnecessary and is another Edison saving in maintenance and operation. In fact, the exclusive use of Edison batteries would eliminate the necessity for and therefore the expense of a battery house. Compare the cleaning out of jars, cutting apart of cells, pouring out solution, removing plates, straightening plates, rinsing plates, and rebuilding the battery. Compare this with Edison cells in service 6 and 7 years, which these expenses cannot occur. Life. The life of any storage battery is generally computed on the number of complete cycles of charge and discharge which it is able to develop. The number of such cycles obtained depends upon the care exercised to keep the battery in good condition and upon such service requirements as would tend to allow the battery to be operated according to the most approved methods. Add distilled water to keep the solution above the plates, the key to lowest maintenance and maximum life. The operating requirements of train lighting service are far from ideal for the battery. Transportation conditions are such that batteries are sometimes completely discharged and allowed to remain in that condition for long periods, and are also very much overcharged at times, both of which conditions cause injurious diseases impossible in an alkaline battery. Edison batteries, which are being tested under purposely imposed conditions designed to shorten their life, have developed over 1,100 complete cycles of charge and discharge and still show a capacity at about 10% above their normal rating. Due to the fact that Edison batteries have been in service 6 and 7 years, are still giving full rate capacity, this company feels justified in making the prediction that when used for train lighting, the Edison battery should still deliver its rated capacity or more after 10 years service. So a little note here from me. This is an early manual from 1916. They didn't find out later, many decades later, the actual expected lifetime, which is far longer, especially with the addition of lithium monohydrate as a component of the distilled water potassium hydroxide alkaline solution. Temperature. For short, infrequent periods, the Edison battery will withstand severe heating better than other types. It is for this reason that numerous batteries have come through fires with no harm except to the rubber parts and wooden trays. But injurious temperatures are seldom met in train lighting, for the rates are almost never very high, and ventilation is usually sufficient in warm weather. The car lighting equipment of the Panama Railroad includes none but Edison batteries. In the matter of low-temperature storage batteries are self-warming. Still air is good. In the matter of low-temperature storage batteries are self-warming. Still air is a good heat insulator. A battery surrounded by still air keeps sufficiently warm for satisfactory operation. In a test made a while ago, an Edison train lighting battery was housed in a tight metal compartment, except for necessary ventilation for gases to escape, but with wind space all around the compartment itself. During a period of 6 weeks of the most severe cold weather, with the temperature averaging 32 below for a considerable part of the time, a recording thermometer indicated that within the compartment the temperature had reached a minimum of 8 degrees below, and throughout the experiment the lights had operated to entire satisfaction. In January 1914, Canada experienced the severest cold weather in 38 years, and yet 42 Edison-equipped cars gave service that completely dispelled all fears of cold. In fact, the road on which these batteries are used has since doubled its Edison equipment, and 3 other Canadian railroads have adopted Edison batteries. Efficiency. The operator of storage batteries does not care so much about what the batteries will do when they are new as what they will do after months and years of service. Theoretical laboratory tests do not interest him. He wants to know how many years he will be able to operate the batteries at a given cost. Here's where other batteries fail. The small battery compartment required by standard Edison train lighting batteries. Almost immediately after they are put in service, they begin to deteriorate. Active material begins to precipitate to the bottom of the jar where it accumulates, and unless it is cleaned out in time, it will short circuit the plates. They're talking about lead acid batteries. This cleaning has been referred to under Maintenance and Operation, page 13. To guarantee such a battery for any period of time is of small value. For even though a new battery be given in exchange or the original price of the battery refunded, the economic loss in time, the interruption in service, and the general inconvenience must be paid for by the owner of the batteries. Contrasted with the shortcomings of other batteries, it is the dependable, sturdy, all-steel alkaline Edison battery. Contrasted with the shortcomings of other batteries is a dependable, sturdy, all-steel alkaline Edison battery. Immediately it is put to work, it increases in capacity. There is no deterioration or corrosion of the plates, and no amount of vibration, jolting, or overcharging will throw down the active material contained in the Edison plate. For this reason, very little sediment space is provided under the plates, and it never becomes necessary to remove the plates from an Edison cell. In fact, they cannot be removed without ruining the container, for the cover is welded on. Standard Edison train lighting battery in compartment required by other batteries. Note saving in space. For some reason it's not focusing. There it goes. Okay. All right. Care. From the operating man's point of view, care has always been a big item. For this reason, the brevity and simplicity of the instructions for the care and operation of Edison alkaline storage batteries, as set forth in our instruction book number 118X, will be appreciated. These may be condensed to 3 simple rules. 1. Add distilled water enough to keep the solution level above the tops of the plates at all times. See page 14. The simple and inexpensive operation is by far the most important of our instructions. Its careful observance will result in maximum life and efficiency. 2. Replace electrolyte with fresh solution at long intervals, probably about 2 or 3 years. So, like I said, it's the early manual, and this is probably before they understood the addition of lithium monohydrate, which extends the life of the alkaline electrolyte. But they say probably, so there's a lot of wiggle room with that. 3. Keep the outside of each cell reasonably clean and dry. Contrast this minimum care and attention with the many operations necessary to the proper care of other batteries. The Edison Alkaline storage battery cut to show construction and installation. Edison Trade Lighting Batteries. Description of manufacture. For trade lighting service, we offer the following 6 sizes. Type A4H, rated capacity 150 ampere hours. Type A5H, rated capacity 187.5 ampere hours. Type A6H, rated capacity 225 ampere hours. Type A8H, rated capacity 300 ampere hours. Type A10H, rated capacity 375 ampere hours. Type A12H, rated capacity 450 ampere hours. The numeral in each case designates the type. The numeral in each case designates the number of positive plates. The letter H indicates high type. As for train lighting, the standard A-type cells are assembled in higher containers, giving about 3 inches of additional space for solution. This feature permits the working of batteries for longer periods without adding water. Attention is called especially to the Edison cell shown on page 18, which is cut to show details of construction and internal arrangement, and should prove an interesting reference for the description that follows. A4H, A5H, A6H, A8H, A10H, A12H. So this video cuts off. I'll just continue in part 2. Positive plate, type A, about 1/2 actual size. The swedged ends of the reinforced perforated steel tubes are permanently secured under the tongues in the steel grid. Negative plate, type A, about 1/2 actual size. Slight grooves in the pockets take the edges of the openings of the grid. Hydraulic pressure of 120 tons presses them into permanent contact and corrugates them. Negative pocket, loaded with iron oxide, 3 inches long by 1/2 inch wide by 1/8 inch thick. Type A, Edison cell assembled, ready to be slipped into container. Positive plate. The active material of the positive plate is nickel hydrate. It is loaded in layers in 1/4 inch perforated tubes formed of spirally wound steel ribbon. alternating with the layers of nickel hydrate, layers of pure nickel flake, 1/16 of an inch square and 4/100,000ths of an inch thick are introduced to increase the electrical conductivity. The hydrate and flake are tamped into the tube in about 300 layers each. When loaded, the tubes are reinforced by eight seamless steel rings equidistantly spaced. 30 tubes properly clamped on the steel supporting grid makes the strongest positive plate ever used in storage battery construction. Negative plate. The active material of the negative plate is iron oxide, mixed with a little oxide of mercury to increase conductivity. It is loaded into perforated rectangular sheet steel pockets and solidly tapered down. When loaded, the pockets are placed in the interstices of the steel supporting grid and forced between corrugated dies into perfect electrical contact under hydraulic pressure of 120 tons. So there's two important elements here for contemporary students of the Edison nickel iron batteries. The legend is that these batteries are environmentally safe, etc. Well, just beware that the early manuals, and this isn't included in later manuals, but I want to make a point. A little oxide of mercury. That's like an activator for the nickel iron chemistry. It's like I'm using the wrong terminology, but it's like an exciter. Okay, and the cousin of the nickel iron is the nickel cadmium. Cadmium has an exciter in it already, so the nickel iron type had to have a little bit of mercury put in to excite it for the reaction to work. So people that think they can make these batteries in contemporary times, just understand you're going to need millions and millions of dollars worth of tooling, expertise, materials. You probably can't make them today here in the United States because the Environmental Protection Agency will hound you. So be aware that these are not the legend that everybody says they are. Found out the hard way. I'm just sharing out with you, save you money and hassle. And so also realize you can't, so there's 2 points I want to make. You can't build these at home. Sorry, you can't. Did you pay attention to the 120 ton press and the all the other little instances? There's a video you should watch as well that I'll probably include in the description. You should watch for more detail. But there's a lot of people that think they can, and I'm not kidding you, there's people that want to get a hold of one of these batteries and they'll take it apart and they'll think they'll get all the secrets by reverse engineering it. Nope, you will not. Just pay attention to the information here. You'll realize, if you're not a half-wit, that your best bet is to restore existing batteries to operable conditions. They're the goose that lays golden eggs. Don't destroy the goose that lays golden eggs. Hydraulic pressure of 120 tons. So all these processes have to be absolutely perfect. Okay, so to make these at home, you are insane. I'm sorry. Assembly of elements. All the plates of like polarity in a cell are slipped over a steel connecting rod through the hole provided for the purpose at the top of the grid. The cell poles are fastened at right angles to these connecting rods. Proper spacing is provided by steel washers of correct thickness, and finally, lock washers and nuts are fitted to the threaded ends of the connecting rod, thus clamping all into a compact unit. The negative element always contains one more plate than the positive element. The positive and negative plates are intermeshed, and small hard rubber pins are placed between to keep them apart. Grooved hard rubber ladders are fitted over the side edges of the plates. These have shoulders at the bottom upon which the plates rest, and perform the double function of keeping the proper distances between the plates and insulating them from the container. Container. The container is a nickel-plated sheet steel corrugated to give it additional strength and then formed by a special machine into the characteristic shape of the cell. The edges and the seams of the container are joined, and the bottom and top are secured in place by means of the oxyacetylene flame, which actually forms the whole container into one piece of metal. Bosses are welded on the sides to hold the cell securely on the tray and keep the cells separated when they are connected up for service. And another step here, I think it's on the video or some other, I read it or saw it somewhere. The actual cases, the nickel plate, part of the process was done in a hydrogen atmosphere. A special assembly or plating room was just a hydrogen atmosphere. So good luck replicating all the manufacture of these. I don't think they can be done today unless you're a multi-millionaire. I'm sorry. Assembly of cell. The elements are shoved in the steel container and sheets of hand rubber are inserted. The elements are shoved in the steel container and sheets of hard rubber are inserted between the outside negative plates and the container to secure perfect insulation. Then the steel top is welded in place. Especially designed hard and soft rubber washers and gaskets are used to provide insulation of the pole openings. The cell is thus securely sealed except for the filler opening. 3 Edison 8H train lighting cells assembled in standard tray. Disconnecting or connecting Edison cells is a simple operation. Gas valve and filler opening. Oh, little bit of note. That's a special tool, and I found a lot of the connectors are really hard to remove. So maybe it's because the batteries I've dealt with are ancient, but it's not easy peasy if you find an ancient set. Gas valve and filler opening. The only opening in the cell that is provided for allowing the gases to escape and for filling. This consists of, let me read that again. The only opening in the cell is that provided for allowing the gases to escape and for filling. This consists of a metal seat upon which rests a hemispherical hard rubber valve suspended from the hinge top, which is provided with a double acting spring that holds it open or closed as required. The valve normally remains seated, thus preventing air or impurities from getting into the cell, but is lifted by the gas as it forms, allowing it to escape. Trays. The cells are mounted in wooden trays, as is shown by the illustration on page 24. The cells assembled in this tray are suspended by means of rubber buttons. One end of the button fits snugly over a metal boss which is welded to the side of the cell, and the other end fits into a recessed board in the side slat. These trays conform to the standard dimensions long ago established for train lighting batteries of other types, and this necessitates the batteries be assembled with unnecessarily large spacing between the cells. Some railroads who use Edison batteries exclusively have found it profitable to depart from the standard practice and save this extra space by using smaller compartments, thus reducing the weight and costs. See page 16 and 17. Edison train lighting battery, 30 volt, 300 ampere hour capacity. It saves 2,000 pounds in weight on every car.